Hi guys, it's Stephen Brock here again, and this is our part 2 of the tutorial. I'm going to be going over the solutions to chapter 28. No, I'm just kidding. Chapter 2, so that's the content that we just covered. Yeah, so the homework question from chapter 2, let's jump into these solutions. Before I get started, I just want to remind you that if you have any questions about any of this material, or still kind of struggling with the content after we go through the tutorial and after I go through the questions, please feel free to send me an email, post a question on Piazza, or stop by during my office hours. I have my email at the end of the slides, but it's steven.brock@mail.utoronto.ca. All right, so let's jump into it. All right, question 1. Let A and B be two events in the sample space for which the probability of A equals 2/3, probability of B is 1/6, and the probability of A intersection B is equal to 1/9. What is the probability of A union B? Alright, well, when you see probability of A union B, one of the best techniques to calculate it is using the union rule. We derived the union rule in the tutorial, so please go back there if you need to review how to derive it. I think it's derived in the textbook as well. Yeah, probability of A union B, we can just use the union rule. And then boom, we got probability of A union B is equal to probability of A plus probability of B minus probability of the intersection. We have all those values. Let's get a common denominator going, and then boom, we get 13/18. So for question 2, let E and F be two events for which one knows the probability that at least one of them occurs is 3/4. All right, so when you see at least one of them, or like one of them is occurring, then we're interested in the union, right? So the probability that at least one of them occurs is 3/4. That means the probability of the union of E and F is 3/4. And what is the probability that neither E nor F occurs? Hint, use one of the De Morgan laws. E complement intersection F complement is equal to the E union F complement. So this is going to be super useful. And I'm hoping that even if they didn't give you this hint, that you'd be able to realize that you could use the De Morgan's law. And even just reading this question, neither E nor F occurs, could sometimes even be interpreted as the complement of E union F, right? Because you have the complement of E union F, and then you know that neither of them occur. So, yeah, so this could have been interpreted just from the question itself. So we have the probability of E union F, which is 3/4, and the probability of E union F complement, which is equal to 1 minus probability of E union F. We showed this result in the tutorial, and it's definitely shown in the textbook, so make sure to review that, because moving from complement, or from the probability of an event to the probability of its complement is a very useful tool. I want to emphasize that again. If you have not memorized how to do that, make sure you memorize / know how to do that. All right, so that just becomes 1 minus 3/4, which is 1/4. All right, so question 3. Let C and D be two events for which one knows that the probability of C is 0.3, probability of D is 0.4, and the intersection is 0.2. What is the probability of C complement intersection D? This is a good time to emphasize, make sure you really read the question. If you missed this complement sign, then you would have thought that, oh, it's just probably C intersection D. Well, they gave that in the question, it's just 0.2. So be careful, that would be wrong. So C complement intersection D. And so when you're working with sets, that's not clear, like right off the start, like how you're supposed to solve this, what equations you're supposed to use, what tools that you've learned you're supposed to implement and remember. Drawing out the Venn diagram is often a great way to solve this. Drawing the diagram representation of the sets and the intersection in this case, or the union, would be very important. So we have probability of C is equal to 0.3, probability of D is 0.4, so this is all the information that we know, and this is what we're trying to find out. And so if we draw a diagram right here, we can see that we have a C here, we have D here, and we're looking for everything outside of C, that's C complement, and that is inside the circle D, and that's just this shaded area here. And we can get this by calculating the probability of D minus the probability, this section right here, which is C intersection D. And so the probability of D minus the intersection is 0.2. All right, moving on to question 4. We consider events A, B, and C which can occur in some experiment. Is it true that the probability that only A occurs and not B or C is equal to the probability of A union B union C minus the probability of B minus probability of C plus probability of B intersection C? So this might be kind of a large thing to look at, or a lot of terms. So let's just start off with this term right here. So again, when you're trying to represent events, how do we do it? How do we represent events? Well, one great way is with a diagram, right? So let's draw the diagram, let's draw our circles, let's draw the overlaps. So here's our diagram right here. We have our A, B, and C, and we're interested in A occurring but not B or C. So we're really interested in this region right here. And so we don't want to have these two B and C circles, right? Well, if you look at it here, the probability of A and not B and not C is just the probability of A union B union C minus the probability of B union C, right? Because that's the probability of these two circles right here. So we can now use our union rule that we've used many times before, and honestly, you're going to need to use this rule a lot in this course, or at least in this section. The union rule is very useful, and it definitely comes in handy. So by the union rule, we can substitute this union for these values, and then we can carry through the negative sign. And we can see that this result right here is this result up here. So yes, it is true. All right, for question 5, the event A intersection B complement that A occurs but not B is sometimes denoted as A minus B. Like, that's how I read that, at least. So here, this backslash is the set theoretic minus sign. And so what that means is that we have our set A, and we're subtracting out every element in B that is also in A. So show that the probability of A minus B is equal to the probability of A minus the probability of B if B implies A. In other words, B is a subset of A. So if you remember from the tutorial, and this is also mentioned in the textbook, that if B is a subset of A, then in our sample space, B is completely enclosed within the event space of A. And so again, how are we gonna write this out? How are we gonna solve this? Well, first, step 1, draw a Venn diagram, right? Draw the diagram. So if we have our event A, we have our event B, and we can see here that the probability of A without B is simply this probability of being in this circle minus the probability of being in this portion, because that's the portion that B is, right? So we can see that we do get that as required. All right, so question 6. When the probability of A equals 1/3, probability of B equals 1/2, and the probability of A union B is 3/4, what is the intersection? Probability of A intersection B, and what is the probability of A complement union B complement? All right, so for the intersection, we can see, okay, we have a union here. We have A, we have B. So some of the things that could be flashing out in your mind and should be flashing out in your mind is the union rule. And the union rule has the union, B, A, and the intersection. So if we rearrange the union rule in a clever way, we can get the probability of A intersection B. And that's exactly what we're going to do. All right, so we have A intersection B is equal to probability of A plus probability of B minus A union B. So we just switched the intersection over to the left side and the union over to the right side. And so we rearranged that with the union rule. And then we substitute our values in, and we got 1/12. 1/12. So for part B, you can notice that, all right, so this is a higher level thinking is to notice that you could use the De Morgan laws here. De Morgan laws are less intuitive, I guess, or less easy to visualize. Maybe that's the right way to do it. But if you draw the diagrams of the De Morgan laws, are pretty easy to understand. But anyways, noticing that you can use the De Morgan law here, when you see complements and unions, De Morgan laws should be coming out in your head. You might not need to use them, but you might want to use them. So in this case, using the De Morgan law makes it a lot simpler for us. So the probability of A of A complement union B complement is the probability of A intersection B all complement. And we can figure that out by using our handy-dandy formula from moving from the probability of an event to the probability of its complement. And so we have 1 minus probability of A intersection B, and this is 1 minus 1/12, which is just 11 over 12. So question 7, let A and B be two events. Suppose that the probability of A is 0.4 and the probability of B is 0.5, and the intersection between A and B is 0.1. Find the probability that A or B occurs, but not both. All right, so A or B occurs. So that should be ringing some bells. That's union, right? Probably that A or B occurs, that's the union of that's probability of A union B, right? But not both. All right, so not quite the inclusive union that we're looking for, but it's exclusive, right? So we want to take the probability that the union occurs minus the probability that both of them occur, which is minus the probability of the intersection of A and B. All right, so I have a let statement here. Using let statements can be very powerful and simplify the amount of writing that you have to do by a lot. So usually when I'm tackling problems, I want to consider a couple things when I first start off. Do I need to draw a diagram? Will a diagram help me? And if it does, then I usually try to draw a diagram first or second. And then also do I need any let statements? So usually when they give you like A and B, like they already give you the let statements, you might not need to have a let statement, but if you're looking for a probability of another event that is kind of messy, A or B, but not both, right? Then sometimes creating your own let statement will help with that. And then after that, once you have a diagram, you have potentially some let statements, then write down what you know. Write down what you know and write down what you're trying to find out. So this is a good example of doing it here. I knew I was going to draw a diagram, so I purposely drew it down here instead of at the top, just to save space. But drawing the diagram first is always a good idea. So let E be the event that A or B occurs, but not both. Probability of A is 0.4, probability of B is 0.5, probability of A intersection B is 0.1. What is the probability of E? That is what we're trying to find out. So the probability of E, we can see from the diagram, is this shaded region, right? Well, that's just the union minus the intersection. So we have our union minus the intersection, and using the union rule, we can substitute the union for probability of A plus probability of B minus the intersection of A and B, probability of the intersection. And since we are already subtracting 1, we have to subtract 2 now. So we can plug in the values that we know, and we get 0.7. All right, so question 8. Suppose events D1 and D2 represent disasters, which are rare. Probability of D1 is less than or equal to 10 negative 6. Probability of D2 is less than or equal to 10 negative 6. What can you say about the probability that at least one of the disasters occurs? What about the probability that they both occur? So I'm just going to take a sip of water, but all right. So what can you say about the probability that at least one of the disasters occurs? When you see at least one, that should be union, right? What about probability that both occur? What should that be? That should be intersection, right? So we're looking at the probability. What can we really say about the probability of D1 union D2 and D1 intersection D2, right? So we're not given a lot of information, but let's see what we can extract. So the probability of D1 union D2, well, we can use the union rule, and that will let us use some of the information provided in the question, right? So probability of D1, probability of D2. Another important thing to note is drawing a diagram representation of D1, D2 of this scenario is also a very good idea and would actually help you understand this question. In fact, I really should have drawn a diagram, the diagram would have made it a lot easier for me to answer and also explain to you guys. But if you're doing this question, I highly recommend drawing a diagram, and I'm going to talk about where the diagram could have been really useful in a second. So using the union rule, the probability at least one occurs is equal to the probability of D1 plus probability of D2 plus the intersection of both of them. We know that the probability of D1 is less than or equal to 10 to the negative 6. Probability of D2 is less than or equal to 10 to the negative 6. And the only thing we know about the intersection is that it's greater than or equal to 0. We don't really know a whole lot else, at least the question's not giving me any more information. So when we're trying to come up with information or extract something that has like a less than or equal to sign, we always want to be conservative, which means that we want to make sure that we don't exclude any of the possible values, right? So in this case, we want to be confident in our answer and we want to be conservative. So we know that we're adding two values that could be 10 to the negative 6, right? And we're subtracting a value that could be greater than or equal to 0, but in the worst, or in the most conservative situation, we want to maximize this whole right-hand side, so this would be 0. And so we know for sure that the probability of D1 union D2 is less than or equal to 2 times 10 to the negative 6. So now, what can we say about the intersection? Well, if we rearrange the equation, rearrange that formula, we can get union on the left. We can get intersection on the left and union on the right. So we know that probability of D1 is less than or equal to 10 to the negative 6. Probability of D2 is less than or equal to 10 to the negative 6. It's this union term that's kind of tricky, and this is where drawing out the diagrams could actually be, or drawing out a diagram could actually be very beneficial. So, as I said earlier, we want to be as conservative as possible. So what that means is that we want our right-hand side to be as high as possible, but not obviously not too high. We want it to be as high as possible, containing all the possible values. So in this case, we want to minimize this union, right? What's the smallest possible union that still works with our definitions? And what's the smallest possible union? Because then that will maximize our probability on the right side because we're minimizing our union. So the smallest union that we can have is if the event D1 is completely within D2 or D2 is completely within D1. And so it's easy to see that with diagrams, and that's why I probably should have drawn out some diagrams here, and when you're solving this, drawing out diagrams definitely helps. But we can see that if one of them is within the other, then the probability of the union is really the max, the probability of the max of D1 or D2. And if we're having the probability of D1 or D2, then that means that one of these D1 or D2 is going to cancel with this probability here, and we're left with the other. And we know that the other has to be 10 to the negative 6. And that is actually the minimum of the probability of D1 or the probability of D2. All right, question 9. We toss a coin 3 times. For this experiment, we choose the sample space. Omega is equal to all this, and these are all the possibilities you can get. There should be 8 of them. 1, 2, 3, 4, 5, 6, 7, 8 that you can get if you toss a coin 3 times. T stands for tails, H stands for heads. So we're going to read these description of sets. So write down the set of outcomes corresponding to each of the following events. So we're going to read this definition and write down all the elements that fall into that event. All right, and then for part B, write down the set of outcomes corresponding to each of the following events. Okay, so these are kind of using the sets that we've made. What can we construct more sets? Or we're going to construct more sets on top of these sets. So it's going to an extra step. All right, so we throw tails exactly 2 times. So these are all the elements here where we have exactly 2 T's. So we have TTH, THT, HTT, and so for B, we throw tails at least 2 times. Well, that's the same thing as throwing it exactly 2 times, but we also want to include when we throw more than 2 times, which is 3 times. So we have 4 elements here. We have TTH, THT, HTT, TTT. For C, this is when tails did not appear before head appeared. That means that we have to have a head first and potentially a tail second. Because if we have only heads, then we still have the statement is still true that a tails did not appear before head appeared. So we have the triple head, we have head, tails, head, head, tails, head, tails, tails. And then for set D, the first throw results in tails. That just means that we're looking at all the outcomes where the first flip was a tails. So that's tails, head, tail, head, tail, and tail, tail. For B, we're now looking at using these sets we've created. So A complement is all the elements in our sample space that are not in A. So that's these 5. We have A union C intersection D. So we want to tackle this brackets first. So C intersection D. Well, that is just the intersection of these 2 sets, and we can see that the intersection is actually empty. And if you look at their definitions, tails did not appear before a head appeared. That means that a head had to appear first, and we might not even have seen any tails. And then D is the first throw was a tails. So if a head had to appear first, then there's no way that a tails was the first roll, was the first flip. So that has to be the empty set. And so A union the empty set, or in fact, any event union the empty set is just that event itself. So this is just A, and then A intersection D complement. Well, what was D complement? D complement is the first throw results in tails. So that means the first throw results in heads. So out of A, how many of these started with a head? Well, just this last element, and that's how we get that. All right, question 10. In some sample space, we consider two events, A and B. Let C be the event that A or B occurs, but not both. Express C in terms of A and B using only the basic operations using intersection and complement. So I feel like we've already seen a question like this not too long ago, like already in this problem set. So C is the event that A or B occurs, but not both. So A or B occurs. That should symbolize or like signal union, right? And not both, that's not the intersection, right? So we're looking at the union minus the intersection again. So we get this, C equals A union B minus A intersection B. And C is the shaded region. Again, drawing up diagram. It's clear that we're obviously looking at the union minus the intersection. So question 11. An experiment has only two outcomes. The first has probability P to occur. The second probability P squared. What is P? All right, so this is one of the harder questions of this problem set. And it's harder because it requires you to use external information or external, formulas that we know. So for example, we know that the probability of any outcome in the sample space happening is 1. All right, so now we know, now we can utilize that the event only has two outcomes. So every time you perform the experiment, it has to be one of these two outcomes. So we can use that, and hopefully we can get a formula that involves only P, and we can isolate and solve for P. So here we go. Let two outcomes A and B. Let the two outcomes be A and B such that probability of A equals P, probability of B equals P squared. So having this let statement at the beginning really helps with the notation, so I don't have to have outcome 1 or outcome 2. I can just be A and B, right? It's just so much easier to write down. So 1 is equal to the probability of omega, which means that every time you perform the experiment, it has to be one of the two outcomes, right? That's by definition of a probability function. And now we know that since there are only two outcomes, the union of the two outcomes is equal to the sample space. So we can make that substitution. And now we can use the union rule to get the probability of A plus probability of B minus probability of A intersection B. And now there's another kind of clever thing that you need to, I guess, observe or note down. And that is actually in the question. That is that these are two outcomes and they're not events. If they were two events, then there could be an intersection. But because they're two outcomes, you can't roll a die and get a 1 and a 6 or a 2 and a 3. Like you have to either get a 1 or a 6 or a 2 or a 3 or a 4 or a 5, right? So the intersection is actually 0, as we can only have one outcome. So we get P plus P squared, which is the probability of B, is equal to 1. So that should signal some a formula in your head back from high school, maybe like some repressed memories, but this is the quadratic formula, right? So, or this is a quadratic equation where we can use the quadratic formula to solve. And we discard the negative root because P has to be positive by definition, or greater than or equal to 0 by definition, right? So we have P is equal to negative 1 plus root 5 over 2, which is approximately equal to 0.618. All right, question 13. In some experiment, first an arbitrary choice is made out of 4 possibilities, and then an arbitrary choice is made out of the remaining 3 possibilities. One way to describe this is with a product of 2 sample spaces. So we have our sample space sigma, or not sigma, omega, which is equal to the product of ABCD times ABCD. So it's all the pairs of ABCD and ABCD. So step 1, make a 4x4 table in which you write the probabilities of the outcomes. And B is describe the event. C is one of the chosen probabilities and determine its probability. So let's write out our 4x4 table. Again, let's start with some let statements to simplify some notation. So A is the first pick and B is the second pick. We'll have A along the columns and B along the rows. We know that if we pick A, we cannot pick A second. If we pick A first, we can't pick, if we pick B first, we can't pick B second. If we pick C first, and can't pick C second. The same thing for D. So the probability of getting those events is all 0. So probability of getting B. Well, that's 1. The probability of getting B in the first pick is going to be 1 over 4. Probability of getting A in the second pick is now 1/3 because we have 3 elements to pick from. So if we multiply those two together, we get 1/12, and we can do that similarly for all of these entries. Another way to solve this is to note that each of these entries is equally likely. And we know that because the sum has to equal 1, the sum of all the possible probabilities of all the possible outcomes is equal to 1, then each of these 12 different entries has to be 1/12. All right, moving on to part B. So this means we picked, this means we picked the C. So C is one of the chosen possibilities. We picked the C first, second, or both first and second. But we know we cannot pick C first and second, so we're just worried about the first and second. So the probability of picking C first is equal to the probability of getting C and A, C and B, or C and D, right? Because those are the only combinations that have C first, which are in this column. And that is 1/4. Similarly, probability of picking C second is all of the entries where we pick C in second spot. So that is also 1/4. And therefore, the probability that C is chosen is probability that you picked it first, plus the probability that you picked it second, which is just 1/2. Question 15. The rule, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. So this is just the union rule that we derive. Is often useful to compute the probability of the union of two events. What would be the corresponding rule for 3 events, A, B, and C? It should start with the probability of A union B union C is equal to probability of A plus probability of B plus probability of C. So, hint, you could use the sum rule suitably, or you could make a diagram as in figure 2.1. When I'm tackling these questions, like 100% diagram every time. You could try to do it mathematically as well. In fact, doing it both ways would really show your understanding, but drawing the diagram is probably the best bet for this. All right, so let's draw the diagram out. We have 3 circles. We have A, B, and C, and we're trying to calculate the union of all 3 of them. Well, the union of all 3 of them is going to be the union of all these circles, but we got to be careful, or it's the sum of probability of A, probability, probability of C, but we have to be careful about the areas or the probabilities that we double counted, just like in the union rule we subtracted probability of A intersection B. So we have that the probability of, this section right here between A and C, we counted that twice because we counted it for A, we counted it for C. We counted this section twice, 1 for B and 1 for C. We counted this section twice, 1 for A and 1 for C. And this middle section we actually counted 3 times, 1 for A, C, and B. So if we subtract out A intersection C, then we will subtract the double counted part here, and we'll subtract one of these double counted parts. We subtract B intersection C, so we subtract this double counted part, and we subtract one more of this double counted. And then we subtract A intersection B, so we subtract this double counted and this double counted. But we actually subtracted this middle section 3 times, and so we need to add that back. And so we add it back in this term. All right, question 16. 3 events, E, F, and G. All right, so question 16 was actually really hard, and it was actually too hard that I'm not going to actually cover it in the tutorial. No, I'm just kidding. I'm going to cover it. So, question 16. It was a little bit tricky, and I think a lot of you guys had trouble with it. So, I'm going to try and go through it and hopefully help you guys demystify the question and hopefully increase your understanding. So we have three events, E, F, and G, and they cannot occur simultaneously. Further, it is known that the probability of E intersection F is equal to the probability of F intersection G, which is equal to the probability of E intersection G, which is equal to 1/3. Basically just saying that all these intersections are 1/3. Can you determine the probability of E? Hint, if you try to use the formula of exercise 2.15, then it seems that you do not have enough information. Make a diagram instead. Alright, so even if it didn't give you this hint, because you got three events going on, like drawing a diagram is going to be very helpful. Alright, so I minimized the question over here. And alright, so there's a lot going on in the diagram that I drew. And I started off by just drawing the three circles, E, F, and G, right? And then I was looking at, alright, so in order to calculate E, I actually just need this section, this section, this section, and this section, right? If I get those three probabilities, then I'm golden, right? So I decided to use some lowercase letters to represent the disjoint sections of this diagram. So we have A, B, C, D, E, F, G, and H. And I wrote here such that A, B, C, D, E, F, G, H are all disjoint. And what else do we know from the question? Well, we know that they cannot occur simultaneously. So the probability of C in the middle is actually 0. That is key for this question. I think at first I forgot to note that down, and the question was a lot harder than I thought. But anyway, so let's start with the let statement, and this is just going to simplify our notation. So let P of x equal the probability of x for any x. We want to know P of E. So this is P subscript E, which is equal to the probability of A plus the probability of B plus the probability of C plus the probability of D, which are these four regions right here. We know from the question, all these 1/3, that probability of B plus probability of C is 1/3, probability of D plus probability of C is 1/3, probability of F plus probability of C is 1/3. So that's the union between F and G, which is C and F, E and F, which is B and C, and E and G, which is C and D. So we'll go through all these equations right here. And since probability of C equals 0, we can eliminate that from this equation, and we get that probability of B is 1/3, probability of D is 1/3, and probability of F is 1/3. If you notice here, we could have actually solved it right away. And that's because if you add these three probabilities, you get 1. And the probability of three disjoint events equaling 1 means that there's no overlap in those 1/3. And that means that these three events actually span the entire sample space. Unfortunately, I did not notice that, and many of you guys maybe might have not noticed it as well. So I'm going to solve it as if we did not know that at this particular point. So we have probability of B, so I checked that off. Oh, the other thing is we do know that the sum of all of these regions, the probability, has to equal 1 by the definition of a probability function. So we have the probability of A plus probability of B plus the probability of C plus probability of D plus probability of D plus probability of F plus probability of G plus probability of H equal to 1. So we have B, C, D, and F. So here we have B, C, and D. We just need the probability of A, really. And so we can substitute those values in. We have probability of A plus 1/3 plus 0 plus 1/3 plus probability of E plus 1/3 plus probability of G plus probability of H is equal to 1. And now if we add these three 1/3 together, we get 1. And if we subtract 1 from both sides, we get this formula. And it was at this point that I realized, oh yes, we did have 1/3. We did have three 1/3s, right? So if we're adding probabilities together and they have to equal 0, well, each of those probabilities has to be greater than equal to 0 and less than equal to 1. And if they're all positive or equal to 0, then in this case, they must all equal 0. Hopefully that makes sense, because if any of these are positive, there's no way this equation could equal 0. So we know that all these are equal to 0, and then now we have our PA, so we can solve for probability of E, which is probability of A plus probability of B plus probability of C plus probability of D, which is equal to 2/3. So hopefully that made sense. Again, I used some of the techniques that I mentioned earlier that you really want to use when you're solving these kind of questions. Drawing the diagram. So I started off by just drawing the diagram. Having some let statements that will simplify notation, and it'll make it a lot easier when you're trying to read over the work that you're doing. All right, moving on to question 18. In a laboratory, 2 experiments are repeated every day of the week in different rooms until at least one is successful. The probability of success being P for each experiment. Supposing that the experiments in different rooms and on different days are performed independently of each other, what is the probability that the laboratory scores its first success experiment on day n? So there's a lot going on in this equation, in this question. Let's just break it down sentence by sentence, right? So 2 experiments, all right? So we might need to have a let statement for each of those experiments. Day of the week, it's repeated every day, different rooms until at least one is successful. So what, at least one, does that ring any bells? Does that mean anything to you? Have you seen this before? Does this signal anything? Well, at least one union, right? So it means one event, the other, or both. So that should be a union. The probability of success being P for each experiment. So if we have some events for these experiments, if we have some let statements, then the probability of success would be P. So we might need to solve for P later in the question, but let's see here. Suppose the experiment in different rooms or on different days are performed independently of each other. Okay, so the experiments are independent of each other, which means if one experiment, the results of one experiment do not impact the results of another experiment. What is the probability that the laboratory scores first success on day n? So this right here, what we're solving for in itself is another event that we would want to create a let statement for. Again, I say that we should consider drawing Venn diagrams for these questions because the sample space that we're interested in the end is the probability of, we're looking at the probability that it takes n days to solve. You cannot really represent that with a sample space because we're working with an infinite sample space potentially, right? We don't know how many n's we have. So let's write some stuff down. So our let statements, let A be the first experiment succeeds, let B be the second experiment succeeds, and let En be the first successes on day n. So an important thing to note here is that making the let statements might not even be that easy, but if you read the question carefully, you can make them in an intelligent way. So we are first considering the success of events, right? So what we want is the event to be successful, or the experiment to be successful, right? So it makes sense to have a let statement for the first experiment being a success and the second experiment being a success, because then we can leverage our probability P, right? So that should be, I guess, maybe kind of intuitive there. And the event that we're interested in is that the experiment takes n days. So that's where our En comes in. The first success is on day n. So let's write down what we know. Probability of A equals P, probability of B equals P, probability of A complement is 1 minus P, probability of B complement is 1 minus P, and we got that using the nifty formula that the probability plus its complement has to equal 1. And we are interested in the probability of En. So when we're trying to solve this, maybe we can recognize some sort of pattern, and that's exactly what we're looking for here. So when we're looking for a pattern, sometimes it helps to draw out, to put in some values for n. So let's just say that n was 1. This is like the easiest case, the base case, right? So the probability of A union B is equal to the probability of A plus the probability of B minus the probability of A intersection B by the union rule. And because A and B are independent, the probability that both succeeds is just the product of both of those probabilities, because the probability of A succeeding does not impact the probability of B. So the chance that they both succeed is the product of the two. So we have 2p minus p squared is probability of A union B. Probability of E2, let's look at that. So that means that we succeeded on, it took us 2 days to get the first success, which means that we must have failed on the first day. So the probability of both failing on day 1 is A complement intersection B complement. And if we notice, we can use the De Morgan laws because we have 2 complements and an intersection or union. We get that this can now become the A union B complement. So the probability of A union B complement times the probability of A union B. And A union B complement is just 1 minus the probability of A union B. We're using that nifty rule again. So we have 1 minus probability of A union B times probability of A union B. Now let's consider 5 days. Let's consider the first success on 5 days. Right? That means that we failed the first 4 and then we got our success. So we have 4 times the 1 minus probability of A union B. We have it on day 1, day 2, day 3, day 4. We failed the first 4 days, and then we have our success, probability of A union B. So we can now raise this term to the power of 4, and then we have probability of A union B. That is the probability it takes 5 A's to succeed. Now, hopefully at this point we can see the pattern. Well, the pattern is this. If we succeed on day n, then we must have failed n minus 1 previous days, all of the n minus 1 previous days. So we now have the probability of En is equal to 1 minus probability of A union B to the power of n minus 1 times probability of A union B. And we can now plug in our values that we have for P, because in the original question, everything was in terms of P, right? They only gave us P and N. So our solution should be in terms of P and N. And so we get 1 minus 2P plus P squared to the power of n minus 1 times 2P minus P squared. All right, last question, question 19. We repeatedly toss a coin. A head has probability P and a tail probability 1 minus P to occur, where P is between 0 and 1. The outcome of the experiment we are interested in is the number of tosses it takes until a head occurs for the second time. So part A, what would you choose as the sample space? And then part B, what is the probability that it takes 5 tosses? So think about that for a second. Our sample space. So we're interested, how many tosses is it going to take until we get the second head? Well, what's the minimum, right? What's like the lower bound? Because it could be any number of tosses, really. So the lower bound, could we get 2 heads in 0 tosses? No, obviously. It'll take at least 2 tosses, right? So we can't do it in 1 toss either. So our lower bound, our sample space, is going to be 2. And because it says until a head occurs, it should be signaling some bells in your head and should notify you that we're really looking at an infinite sample space here, right? Because we could get the first head after 1 toss, but the second head, that could take infinitely many tosses, right? In fact, the first head could also take infinitely many tosses. So the upper bound of the sample space is going to be infinite, or really all the positive integers greater than 2, right? So let's jump into the solution. And what is the probability that it takes 5 tosses? All right, so because the minimum number of tosses is 2, we have that our sample space is 2, 3, 4, all the way up to infinity. And for part B, let En be it takes n tosses, so we're having a let statement. The probability of E5, that is what we're interested in. So consider E5. We know that the last roll is a head. The first 4 tosses, therefore, can contain 1 head and 3 tails. And so this can happen in one of the following ways. Either we have the head first and then 3 tails, or we have a tail, then a head, and then 2 tails, or we have 2 tails, a head, and then a tail, or we have 3 tails and then a head, and then the last flip has to be a head, right? So since these outcomes are all independent, right, you can't have 2 of these outcomes, it has to be just one of them. The probability of E5, E subscript 5, is equal to the probability of the sum of the probability of each of these individual events. And we can see that the first event is head, tail, tail, head, head, tail, 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 head. So that's P, 1 minus P cubed, and then P. Then we have tail, head, 2 tails, and then a head. So that's 1 minus P, P, 1 minus P squared, and a P. And we can do that for the rest of the 2. And we can notice by using the commutative property that we can rearrange the terms. And each of the terms has 3 1 minus P's and 2 P's. So we get 4, because there's 4 of these terms, 1 minus P cubed times P squared. And I have a bonus on the next slide, and I highly recommend sticking around for that bonus. All right, so here's the bonus. The 2.19 aside, it's not a bonus question, this is a bonus note. So it's an important thing to note, and it might come in handy. There might be a midterm or final question revolving around this stuff because it's a lot trickier and it involves a higher level of understanding and being able to remember some of the concepts that you've learned previously. So in general, consider e to the n. For n greater than or equal to 2, n belongs to the integers. We have that n flips. Which are x1, x2, we're going to call all the way up to xn. And we know that xn equals h, so that's the last flip. And 1 of xi equals h for I is in 1 to n minus 1, right? One of those previous x's had to have also been a heads. The rest are tails. Therefore, we have n minus 1 choices to put the first h, right? If we're looking at all the different combinations, right? So combinations, choices, that should invoke your knowledge of combinatorics that hopefully you learned back in high school. So if we have n minus 1 choices for h, right? So it can be in the first position all the way up to the n minus first position. And so that is n minus 1 choose 1, that kind of notation. Times, we know we have n minus 2 tails, and we have 2 heads, so that's where our p squared comes in. And so the probability of en is actually n minus 1 times the probability of 1 minus p to the power of n minus 2 times p squared. And that's just the general formula for e to the n. Understanding how I got this is a higher level understanding. But if you can kind of reason with it and understand it, it'll really help you with probability in this course. If you still don't understand it, feel free to, again, shoot me an email or post a question on Piazza or drop by during office hours. I'd love to talk about this. Another question that could be asked on potentially a quiz or a final or a midterm is, what if the number of heads that we're looking for is a variable? So we're interested in the number of tosses before k heads, for example, right? How would you represent that formula, or how would you represent that probability? So think about that. It's very similar to what we currently have, but maybe with a couple substitutions. Yeah, and that is everything for the tutorial. So if you still have any questions, feel free to post them on Piazza, send me an email, or stop by during office hours. And I also want to say that I appreciate any positive or negative feedback on the tutorial as well. This is actually my first time being a TA for any course, so I know that there's some things that I could do better, and I would really like to know if you enjoyed some of the things I did, if you didn't enjoy some of the ways that I went through questions or the way that I went through the tutorial. Thank you very much, and best of luck with your studies.